Welcome to review lecture number 7 in our online review course of undergraduate probability and statistics. I'm Chris Mack, your professor for this class, and we're going to discuss a new topic, discrete random variables. We're going to begin by introducing random variables in general. What is a random variable? What is it used for? I'll talk about it a little bit formally using mathematics, but mostly I'll try to emphasize its practical meaning and use. Nonetheless, the formal definition will be important because we're going to use some mathematics of random variables a lot in what's going to follow in our class in statistics. As we've seen before in our last 3 lectures on probability, we create a probabilistic model. This model is up to us to make. It depends on our knowledge of the system we're trying to model, and it assigns probabilities to events. Events are collections of outcomes that come from our sample space. We always create probability models and laws that obey the 3 probability axioms. And we've studied what those were. All of these events, outcomes, and sample spaces that we're discussing here are represented mathematically by sets. We can think of these sets as being either finite or infinite and represent either discrete or continuous variables, but they're all sets. In science, our models tend to be mathematical. They deal with numbers. By mathematical, I mean the algebraic and applying calculus, etc., the normal non-set mathematics that deal with numbers rather than sets. So we need something to map the sets of our events, outcomes, sample spaces that we've defined probabilities around and turn them into numbers. That's where a random variable comes in. A random variable is a real valued function of the outputs of an experiment. It maps the sample space onto the real numbers so that we can turn our sets of events, outcomes, sample spaces into numerical values. So in a very formal mathematical way, if we have some element, little omega, of the sample space, big omega, then our random variable x will map an element in the sample space to a number, where this number x is a member of the real numbers. Well, that sounds all kind of fancy mathematical, but here's a real simple example. Suppose my sample space are all UT students, and what I want to do is discuss the height of the UT students and then do some calculations such as the mean height or the standard deviation of the heights, etc. Well, our random variable x will define as a height of a randomly selected student. So it's mapping the student to a number that represents the height. We can sometimes think of these random variables as measurements. In fact, that will be one of the most common applications of random variables, as measuring from an outcome of an experiment. Now, there are 2 kinds of random variables, discrete and continuous. Let me give you some examples using, well, this previous example of the height of a randomly selected UT student. We could take that height and round the measurement to the nearest centimeter. Well, if we then looked at all the heights from all the students from short to tall, we would have a reasonably small number of heights, right? Maybe 20 or 30. I don't know exactly how many, but a very finite number of discrete numerical values. However, we could think about or model the measurement as having infinite precision. If I were to measure the height of that randomly selected UT student to infinite precision, the result would be a continuous random variable. That is, a random output of that measurement, a random variable a random value for the random variable would be a number anywhere on the real number line. In reality, this can never happen. When we're talking about measurements, we can never measure with infinite precision. Nonetheless, we'll often assume that we can in order to model our random variable as being continuous, because there's a lot of nice properties and qualities of dealing with continuous random variables that make them much more convenient than a very large number of discrete random variables. Nonetheless, most of our problems will very naturally fall into the categories of discrete versus continuous. I'm going to talk about discrete random variables for the next couple of lectures. Then we'll talk about continuous random variables after that. Let's look at some random variable examples. Here are examples of random variables, some of which happen to be discrete and some continuous. Examples: the number of heads in a sequence of 12 coin tosses. The sum of 2 rolls of a die. The number of coins until the first head is obtained. The money I won or lost in a particular game of chance. Very much depends on your knowledge of probability, how much money you'll win or lose in a particular game of chance, I think. And the time required for a text message to travel from sender to receiver. Now, of all of these, most of them that I've picked are discrete, certainly the first 3. The fourth one, the money won or lost in a particular game of chance, is in fact a discrete random variable as well, since our money is in increments of pennies, for example. But it's often convenient to model that random variable as a continuous random variable instead. The time required for a text message to travel from sender to receiver would generally be modeled using a continuous random variable. We use slightly different mathematics when we handle discrete versus continuous random variables, and as you'll find out as you work through some problems over the next few lectures, the continuous random variables are actually a bit easier to deal with. Nonetheless, there's plenty of times when we need to use discrete random variables, and that will be the topic of today's lecture. The most important mathematical function that defines for us our probability laws using the random variables rather than the sets of outcomes and events is the probability mass function. For a discrete random variable, the probability mass function is here, P of x, P sub x rather. The capital X is the random variable, and then the little x is the value that that random variable obtains when we actually perform an experiment. And this PMF, probability mass function, is defined as the probability of the event that the random variable x takes on the value of little x. So you can see that we're mapping an event, which could be a single outcome or it could be something more complicated, but it is the probability of a particular event happening, and we turn it into a mathematical function, P sub x, evaluated at little x. We tend to use quite rigorously the capital letter X to represent the random variable, and the little x to be the real number, the value that random variable takes. For example, let x be the sum of 2 6-sided dice. I roll 2 dice, and I get a number when I sum up the number of spots that come up, and now I'll ask what's the PMF for this random variable. Well, the sum of 2 dice will have values that go from 2 to 12, and I can use the reality that if I have fair die, then the probability of each one coming up with a specific number is 1/6, and I will simply enumerate all the possibilities and use the uniform probability law to determine the probability of each outcome. The outcomes are 2 through 12, and when I evaluate the probability, I can define my PMF for each value. Note that when I sum up the PMF over all possible values for my random variable, I will get 1. That's part of the probability law axioms. Now, let's take this idea of a random variable and define a very specific random variable which we'll give a name. It'll be the Bernoulli random variable. Consider an experiment that can only have one of two outcomes. For example, I flip a coin and I can have a head or a tail. Only two outcomes. If the head has a probability of occurring of p, then I will define my random variable as such. And this is called a Bernoulli random variable. X is 1 if I get a heads and 0 if I get a tails. We'll often use the phrase success and failure. I'll define a success as getting a 1 and a failure as getting a 0. Often these terms success and failure don't have anything to do with moral judgments of what's good or bad. Just randomly assign one of them to be a 1 and the other to be a 0 and call one a success and the other a failure. If I wanted to, I could flip the definition of what's a head and what's a tail, what's a success or what's a failure. Wouldn't make any difference. So don't let these terms success and failure fool you. They're just names that we've used historically. So a Bernoulli random variable is binary. It takes on the values of either 0 or 1, and the probability of getting a 1 is p. So our PMF for the Bernoulli random variable is a value of p if k equals 1 and a value of 1 minus p if k equals 0. So the PMF of 1 is equal to p. The PMF of 0 is equal to 1 minus p. This Bernoulli random variable is used to model many, many different binary outcome experiments. There are plenty of experiments where the outcome is either 0 or 1, success or failure. Often, these binary outcome experiments will be repeated. We talked about independent trials a couple lectures ago, and an independent trial is a trial where the probability of success for that trial is a constant, and every trial is independent of every other trial. When we have a Bernoulli random variable that's repeated over and over again, and the probability of success remains constant and independent of the outcome of any other trial, we call those trials Bernoulli trials. And if we have Bernoulli trials, we can generate something called the binomial distribution. Let's repeat a Bernoulli trial n times. We'll let p be the probability of success. And we'll ask, we'll first define, a new random variable, x, as being the number of successes. So I repeat the trial n times and I ask, how many times did I get a 1? How many times did I get a success? The binomial distribution says the PMF of getting k successes out of n trials goes like this. Now, look at this. We have a notation, n choose k. We've seen that before, haven't we, in our combinatorics analysis. Where might this binomial distribution have come from? Well, let's look at it. I repeat a Bernoulli trial n times. The probability of success is p. If I get k successes, that means I got p probability k times. So that happens with likelihood p to the k. And then I got failures, 1 minus p, the other times, which is n minus k. So a sequence of ones and zeros, successes and failures, heads and tails, for example, any sequence of k heads and n minus k tails, k successes, n minus k failures, will have a probability of occurring of p to the k times 1 minus p to the n minus k. But if the sequence doesn't matter, the order doesn't matter, then I ask how many different sequences are there of k successes from n trials? And the answer to that is n choose k. Since they're all have identical probability, I can simply add them all up, and that gives me my total probability. And that's how we derive the binomial distribution. It assumes that n is a constant. Sometimes the number of trials can be a random variable. When that happens, then we don't have a binomial distribution. N has to be fixed and known ahead of time. Then we have all the assumptions of a Bernoulli trial. P is a constant, and it's independent of whether or not other trials had certain outcomes. So independent and constant. The result is two parameters in the binomial distribution, n and p. Another important distribution is the geometric distribution. How many times do I need to toss a coin before I get the first head? So if I have an experiment where I keep tossing the coin over and over again until I get a head, and then I stop, you might ask, what's the probability of me tossing the coin once? What's the probability of having to toss the coin 4 times before the first head comes up? Well, we can easily figure that out. Just think about, again, a staged counting problem. And I say, let my random variable x be the number of tosses to get the first head. The probability of x being equal to k, well, I have to have first a sequence of k minus 1 failures followed by 1 success. Right? That's the only sequence possible. And therefore I can easily calculate what the probability is of having k tosses before my first head comes up. And again, this is called the geometric distribution. Another interesting distribution is the Poisson distribution for discrete random variables. The Poisson distribution is derived from the binomial distribution for a special case. The case when n is much, much bigger than k. And this is, again, a common occurrence. We can, in fact, let n go to infinity. In fact, if we let n go to infinity while keeping np a constant, the number of trials multiplied by the probability of success for each trial, if we let that product be a constant, and then we let n go to infinity, what's going to happen? Well, my binomial distribution in the limit as n goes to infinity, well, it takes a little bit of math to do this, but we could work it out, and we find that we get this interesting result called the Poisson distribution. I've got e to the minus lambda, lambda to the k, divided by k factorial. This is the probability of getting k successes when np equals a constant. It's called the Poisson distribution. Here's a very simple example. I've got a solution with a concentration C. Then I look at a small volume V and I ask, how many molecules are in that volume? Well, it's a random distribution. We don't get the exact same number of molecules. We get an average number of molecules, though. What's the average number of molecules? Well, you might expect it to be C times V, and you'd be right. So our parameter lambda is the concentration times the volume. This is turns out to be the mean number of molecules I'll have in that volume when the solution has a certain concentration C. But in fact, I could have more or less. And the probability of getting exactly k molecules in that volume will be given by this Poisson distribution. A couple more things about random variables. Sometimes we have to take a function of a random variable. Functions of random variables are random variables themselves. For example, suppose I'm given a random variable x and its PMF here. Then I also have a mathematical function, y equals g of x. My question is, what is the PDF of the random variable y? Well, we can easily figure that out. First, I find all the x such that g of x is equal to y. There might be one x only, but there might be a lot of different x's that produce the value y. And once I've found all the values of x such that g of x is equal to y, then I sum up all their probabilities from the PMF, and that gives me the PMF of the value y. This applies for x and y both as discrete random variables. One last thing, important topic. We've talked about the probability mass function, or PMF. Now I'm going to talk about the cumulative distribution function, or CDF. We've seen before that a random variable, when it's discrete, is characterized by its PMF. The PMF is simply the probability that the random variable takes on a particular value, x. We also know that if I sum up the PMFs for all x, I will get 1. We now define the cumulative distribution function. I'll use the capital letter F instead of the small letter p, like we did for the PMF. The cumulative distribution, capital F, will be the probability that our random variable x is less than or equal to some number. How can we figure that out? Well, we simply sum up all the probabilities for all the k that are less than or equal to x. Sum up all those probabilities, that is the cumulative distribution function. Well, we've gone through some properties of random variables, and in particular discrete random variables, and we looked at some example probability mass functions with interesting names like the binomial distribution, geometric distribution, and the Poisson distribution. These will turn into valuable distributions that we can use in real life problems. Right now we're just thinking of it pretty much as a mathematical exercise, but they will have real world practical applications. So let's review what we've learned. As always, you should be able to quickly and easily answer these questions. If not, please go back and review the material again. Define random variable. Explain the difference between discrete and continuous random variables. What is the PMF, the probability mass function? What is a Bernoulli trial, and what assumptions apply? Can you explain the binomial, geometric, and Poisson distributions, where they come from? And finally, define the cumulative distribution function. Next time we'll calculate some statistics based on these probability distribution functions that we've discussed so far. And until then.